Hello, and welcome back to Sleepy Wiki. As you settle in, gently allow your shoulders to drop and feel your breath soften, slowing to a peaceful rhythm. Tonight, we'll drift on the edges of the unknowable, journeying not through the cosmos as we know it, but into the profound stillness that may have existed before it all began. Imagine, if you will, a vast, unformed quiet, a universe yet to awaken, where time itself held no meaning. We'll explore the whispered theories and poetic imaginings of what lay in that primordial void, that moment before the grand symphony of creation. It's a journey into pure potential, a gentle contemplation of the ultimate beginning, or perhaps the ultimate absence. Let these ideas simply wash over you like soft waves on a distant shore as we explore the profound mystery of what came before. If these gentle wanderings bring you a moment of calm, perhaps consider softly tapping that like button or subscribing to join our sleepy community, so these quiet stories can continue to find you. Now, as we prepare to step into that deep, hushed expanse, let your mind drift, unburdened by the need to understand, only to be. Before the Big Bang, what was there? It's a question that whispers through the very fabric of our understanding, a mystery veiled in shadow and cosmic dust, inviting our minds to journey to the outermost edges of knowledge. We often speak of the Big Bang as the ultimate genesis, the moment our universe ignited into existence, a singular point of creation. And indeed, for physicists, it represents not just the beginning of all matter and energy, but also the startling commencement of space itself, and most profoundly, the very unfolding of time. It's as if the cosmic clock didn't exist until that profound moment, ticking into being alongside everything else. Imagine standing by a river, but this river isn't just carrying water. This river is time. The Big Bang isn't merely a point on that river, an ancient marker along its banks. Instead, it's the very source from which the river begins to flow. Asking what happened before the Big Bang might then be akin to asking what's north of the North Pole, or what lies beyond the edge of a circle. The question itself, in this context, might become a linguistic trick, because if time originated with the Big Bang, then before might simply not be a meaningful concept in the temporal sense that we understand. Yet, our curious minds, always seeking to trace paths backward, push us to explore. At the heart of the standard Big Bang theory, if we could wind the cosmic clock backward with perfect precision, we would arrive at an incredibly dense, unimaginably hot state, a singularity. Picture all the vastness of our universe, all its stars, galaxies, and empty spaces compressed into an infinitesimally small point. At this theoretical singularity, the laws of physics, as we know them through Einstein's general relativity, begin to break down, like trying to read a map where all the lines converge into an indistinguishable, blurry dot. Our mathematical tools, so powerful in describing the universe's expansion, simply tell us, we can go no further here. It's a boundary, not necessarily an end. We can, however, peer back with our mathematical instruments to an epoch incredibly close to this theoretical beginning, a whisper of a moment known as the Planck Epoch. This is a sliver of time almost beyond human comprehension, an unimaginably brief fraction of a second. 10 to 43 seconds to be precise. During this epoch, the universe was so compressed and energetic that the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces might have been unified, indistinguishable from one another, like threads of a single vibrant tapestry, not yet unraveled. It's a moment so tiny, so extreme, that the very concepts of smooth space and continuous time might have been shimmering, undefined, like water at the edge of freezing, or a blurry photograph struggling to resolve itself. But what if there was something in some form before this? This is where scientific imagination truly takes flight, guided by the tantalizing hints that our current theories leave us. Some scientists ponder the idea of a cyclic universe, an eternal cosmic rhythm of expansion and contraction. Imagine a giant universal heart, breathing in and breathing out across epochs. In this vision, often called the Big Bounce, our universe didn't necessarily begin from nothingness, but rather emerged from the dramatic cataclysmic collapse of a previous universe. That prior cosmos might have reached its maximum expansion, then slowly contracted back down, compressed into an incredibly dense state, only to reach a critical point and rebound, springing back open to begin anew. It's like a cosmic pendulum, swinging endlessly through states of compression and expansion, each swing birthing a new iteration of existence, carrying forward perhaps some echoes or remnants from its past. Another profound idea paints our universe as merely one bubble in an endless frothy sea of universes, a multiverse. In this captivating scenario, something called eternal inflation never truly stops. Imagine a vast, ever-expanding ocean of space-time inflating relentlessly. Within this ocean, tiny pockets might occasionally pinch off, like steam bubbles rising from a boiling pot, each forming a new bubble universe with its own Big Bang, its own unique set of physical laws, its own flow of time. Our observable universe would then simply be one of these countless nascent bubbles, born from an ongoing, larger, and perhaps eternal inflationary process. The before then becomes a beyond, a vast parent landscape of quantum fluctuations and energy from which our universe and countless others spontaneously emerged. It suggests a universe far grander, far more populous than we can possibly conceive. Then there's the fascinating realm of loop quantum gravity, an attempt to bridge the divide between Einstein's general relativity and the quantum world. This theory suggests that space-time itself isn't a smooth, continuous fabric, but rather is made of tiny, discrete loops or atoms of space, much like a knitted sweater is made of countless individual threads. At the point where a classical singularity would form, these fundamental loops or quanta of space prevent infinite compression. Instead of collapsing into nothingness, the universe reaches a minimal but non-zero volume before experiencing a quantum bounce. It's like trying to squash a sponge indefinitely. It can only get so small before its internal structure resists further compression and then springs back. This suggests a smooth transition, where our universe emerged directly from a prior contracting phase without ever encountering a true singularity where physics breaks down. It offers an elegant solution to the beginning problem, transforming it into a moment of rebirth rather than absolute creation. These aren't easy concepts, are they? They push the very limits of our imagination and our mathematics, forcing us to reconsider our most fundamental assumptions about existence, time, and space. But what a magnificent journey it is to stand at the edge of the unknown and simply wonder, to ponder possibilities that stretch beyond our direct experience into realms of pure theory and profound speculation. It's a testament to the insatiable curiosity that drives us to ask, to explore, and to dream of what lies beyond the veil of what we can currently perceive. As we drift gently away from these profound and mysterious beginnings, from the very edge of before, let us next turn our thoughts to the very first moments after the Big Bang, to the incredible dance of light and energy that began to shape the infant cosmos. We will explore the universe's first breath after its magnificent birth as it started its grand journey of becoming. The universe, our vast and wondrous home, has a story that stretches back further than we can truly grasp, a story whispered in the oldest light and the most fundamental particles. But even before the grand crescendo of the Big Bang, before the universe began its magnificent expansion, lies a period so profoundly mysterious, so utterly alien to our everyday experience, that it demands we gently set aside the familiar rules of physics. We journey now to the very threshold of creation, to a moment known as the Planck Epoch, a realm of such exquisite mystery, it feels less like a beginning and more like an eternal, shimmering enigma. Imagine standing at the edge of an ancient, swirling fog, so dense and opaque that it obscures everything beyond. This fog is the Planck Epoch, the first fleeting fraction of a second in the universe's life, from time 0 up to approximately 10^43 seconds. Within this incredibly brief flicker, all of our comfortable understanding of space, time, and gravity simply dissolves. The laws of physics, the very framework that allows us to predict the dance of planets and the glow of distant stars, crumble like sandcastles before an immense tide. It's not that these laws are wrong, but rather that they are incomplete, unable to describe a universe so infinitesimally small, so inconceivably hot, so extraordinarily dense. At this primordial moment, the entire observable universe, or rather the tiny seed from which it would blossom, was compressed into a space far smaller than a single atom, perhaps even smaller than the smallest subatomic particle we know. Think of it as a cosmic pinpoint, an ultimate singularity of infinite density and temperature, predicted by Albert Einstein's majestic theory of general relativity. But as we peer into this pinpoint, general relativity, which describes gravity as the curvature of space-time, falters. Its smooth, elegant equations break down when matter and energy are squeezed into such an unimaginable concentration. It's like trying to draw a perfect circle on a violently bubbling, frothing surface. The very concept of a smooth line loses its meaning. To navigate this turbulent cosmic sea, we need a new kind of map, a theory of what's called quantum gravity. While general relativity works beautifully on large scales, quantum mechanics rules the microscopic world, describing particles as probabilities and energies as discrete packets. The Planck Epoch is the intersection where both theories should apply, but they clash, like two grand symphonies played simultaneously in different keys. The universe was so small, and its energy so immense, that the quantum fluctuations of space-time itself would have been paramount. Space-time, usually thought of as a smooth, continuous fabric, would instead have been a chaotic, churning foam, a space-time foam, as some physicists vividly describe it. Imagine not a placid river, but a tumultuous, boiling cauldron where new dimensions might briefly flicker into existence and vanish, where the very concepts of up and down, before and after, lose their customary anchors. In this superheated, superdense state, the fundamental forces of nature, which we now know as four distinct entities, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to have been unified. Picture them not as separate entities, but as different facets of a single primordial superforce, like various colors that emerge from a single beam of pure white light. It was a moment of perfect cosmic symmetry, a singular, harmonious chord played on the universe's grand piano. As the universe began its infinitesimally brief journey out of the Planck Epoch, this superforce would begin to cool and crystallize, leading to a series of symmetry breaks, much like water freezing into ice or a single color separating into a spectrum. First, gravity would differentiate, then the strong nuclear force, and finally the electromagnetic and weak nuclear forces, setting the stage for the rich and varied universe we observe today. The Planck Epoch is not just about extreme conditions. It's about the very nature of existence. It gives rise to a profound question, the ultimate before. What, if anything, came before the Planck Epoch? What lies beyond that shimmering veil of fog? Here, science steps beyond observable data and into the realm of profound, elegant speculation, guided by mathematical beauty and philosophical insight. Was there a before at all, in the sense we understand time? Perhaps time itself, as we experience it, emerged from this epoch, rather than existing prior to it. Some theories, like the no-boundary proposal from Stephen Hawking and James Hartle, suggest that the universe didn't have a sharp, definable beginning in time, but rather emerged smoothly, like the surface of a sphere has no edge, yet is finite. There would be no point where time started in a conventional sense, but a gradual transition from a state where time behaves more like a spatial dimension. Other ideas paint a picture of a universe that is part of a larger, grander cosmic ballet. Could our universe be just one bubble in an infinitely vast multiverse, an ocean of countless realities, each with its own laws and origins? In this view, the Planck Epoch might not be a unique beginning, but a local unfolding within an eternal, overarching cosmic foam. Or perhaps, as proposed in some cyclic models, our universe is but one iteration in an endless cycle of expansion and contraction, a cosmic heartbeat that has pulsed through eternity, with each Big Bang arising from the collapse of a previous universe, passing through a Planck-like singularity. Each collapse and rebound is a cosmic reincarnation, a phoenix rising from its own ashes. Then, there are the tantalizing whispers from string theory, a framework that proposes that elementary particles are not point-like, but rather tiny, vibrating strings of energy. At the Planck scale, these strings, along with perhaps extra hidden dimensions, would have played a dominant role. The Big Bang itself, in some string theory scenarios, might be the result of a collision between two brains, colossal, membrane-like structures existing in higher dimensions. The Planck Epoch, in this context, becomes the moment of profound interaction, where the fabric of reality was being woven from these fundamental, vibrating threads. These are not answers, dear listener, but magnificent questions, illuminating the boundary between what we know and what we are striving to understand. The Planck Epoch remains a profound enigma, a whispered secret at the very dawn of creation, beckoning us deeper into the story of the cosmos. As we drift beyond this edge of understanding, the universe begins to take on a more familiar shape. As the unified forces start to separate, and the cosmic soup begins to cool, making way for the first light to shine, and the first structures to form. And it is to that radiant emergence, the universe's earliest light show, that we shall turn our thoughts next. Our cosmic journey often begins with the whisper of the Big Bang, a moment of unimaginable intensity, the fiery dawn of everything we know. But even in that grand narrative there lies a profound mystery, a cosmic knot that science gently seeks to unravel, the Big Bang singularity itself. Imagine trying to read a story where the very first page is blank, or perhaps infinitely dense. That's a little like how physicists feel about the singularity. According to our most trusted theory of gravity, Einstein's general relativity, if we rewind the universe's expansion far enough, we arrive at a point of infinite density, infinite temperature, and zero volume. This is the singularity, a place where the laws of physics, as we currently understand them, simply break down. It's like reaching the edge of a map where the landscape dissolves into an unreadable swirl, a place where our equations no longer have meaningful answers. But the universe, in its elegant wisdom, often shies away from true infinities, especially those that defy logical explanation. So a new quest began, a gentle exploration into what might have truly happened before that singular point, or what might have resolved it. This quest is deeply intertwined with one of the greatest challenges in modern physics, unifying general relativity, which describes the very large, stars, galaxies, the universe, with quantum mechanics, which describes the very small atoms, subatomic particles. This is the search for a theory of quantum gravity, and it is from this quest that our Singularity Resolution Models emerge, like soft light piercing through the cosmic veil. One such vision comes from a theory called loop quantum gravity, LQG, and it offers a concept beautifully known as the cosmic bounce. Imagine, if you will, that space and time aren't perfectly smooth, continuous canvases. Instead, picture them as being woven from incredibly tiny fundamental threads, like a fine cosmic tapestry. These threads are so infinitesimally small that they appear smooth on our everyday scales, just as a fabric appears smooth from a distance, even though it's made of individual fibers. In this framework, the universe couldn't just collapse to an infinitely dense point. The very structure of space-time, these fundamental threads, would resist it. Like a spring that can only be compressed so far before it pushes back, the quantum nature of gravity suggests there's a minimum possible volume the universe could have. Instead of collapsing into a singularity, a preceding universe might have contracted down to this incredibly tiny but finite size, a state of extreme density, yes, but not infinite. And then, rather than an abrupt end, it gently rebounded. This minimum volume acted as a cosmic trampoline, launching the expansion of our universe. The Big Bang, in this view, isn't a singular beginning from nothing, but rather a grand echoing rebound from a previous contracting cosmic era. It's a universe that breathes in and out, an eternal cosmic heart that beats, never truly reaching a zero point, but always transforming. Then we turn our gaze to another captivating idea, rooted in key string theory and its grander extension, M-theory. Here, the universe might be far richer in dimensions than the three spatial ones we perceive, plus time. Imagine our entire observable universe as a single brain, a vast, thin membrane existing within a higher dimensional space, much like a single sheet of paper floating in a larger room. These higher dimensions are usually curled up so tightly we can't detect them, like an incredibly fine strand of hair that appears to be one-dimensional from a distance, but has a tiny width and depth when viewed up close. In this brain cosmology, the Big Bang might not have been a point, but a cosmic collision. Picture two enormous, multidimensional brains drifting through a higher dimensional space, perhaps unaware of each other for eons. Then, ever so gently, they touch, they graze, they collide. This immense collision, this brushing of cosmic membranes, releases an incredible burst of energy, creating the matter and energy that we associate with our Big Bang. It's like two giant silent gongs suddenly sounding across the void, their reverberations giving birth to our cosmic symphony. This model can even suggest a cyclical universe where these brain collisions happen repeatedly, leading to an endless series of big bangs and big crunches, a cosmic dance of approach and recession, echoing through vast, unseen dimensions. Another breathtaking perspective emerges from eternal inflation and the concept of the multiverse. Here, the period of rapid expansion known as inflation, which smoothed out and expanded our early universe, isn't a one-time event that ended everywhere. Instead, it's an ongoing, ever-present process in a much larger background multiverse. Our Big Bang, our observable universe, is simply one bubble that nucleated and separated from this eternally inflating background. Picture a vast, frothing ocean of space-time, constantly bubbling and boiling, with new universe bubbles forming all the time, each with its own Big Bang. In this scenario, there's no single beginning for the entire multiverse. Inflation simply never truly stops, continuing to create new regions of space and new universes, like an infinite garden constantly blooming with new, unique flower universes. Our Big Bang is merely the birth of our particular flower within an unimaginably grander, ceaselessly creating cosmos. Finally, let us consider a truly elegant, albeit abstract, idea proposed by Sir Roger Penrose, known as conformal cyclic cosmology, CCC. This theory suggests that the universe cycles through an infinite series of eons, where the infinitely distant future of one eon becomes the Big Bang of the next. Imagine a universe that expands, cools, and empties out over unimaginable timescales. All matter eventually decays, black holes evaporate, and all that's left is radiation and gravity. At this point, the universe becomes conformally flat. Essentially, it loses all sense of scale and mass. What becomes important is only angles and relationships, not absolute size. In this state, an infinite future in one eon is mathematically identical to a singularity in the next. The end of one universe, a cold, empty expanse, smoothly transitions into the hot, dense beginning of another, without information ever being truly lost, just transformed. It's like a cosmic melody that fades to silence, only to echo again, transformed, as the opening notes of a new grand composition. The universe breathes, not just in volume, but in a profound transformation of its very essence, an eternal cosmic recycling of existence. These singularity resolution models are not mere fanciful tales. They are the frontier of our understanding, born from the very equations that describe our universe. They offer profound comfort, suggesting that the universe might not begin with an abrupt, incomprehensible infinite point, but rather with a sophisticated, elegant transformation, a bounce, a collision, a bubble, or a cosmic rebirth. They paint a picture of a cosmos that is perhaps more ancient, more interconnected, or more continuous than a simple on switch. They remind us that the story of existence is far more intricate and wonder-filled than we can often imagine. As these elegant resolutions settle in our minds, another intriguing question emerges. What if the universe's story has no true beginning at all? What if existence follows an eternal rhythm, cycling through endless transformations? The very phrase "before the Big Bang" sends a shiver of wonder through the fabric of our understanding, doesn't it? For so long, the Big Bang has been the curtain rising on the cosmic play, the singular beginning of everything we know. It describes how our universe expanded from an incredibly hot, dense state, leading to the stars, galaxies, and even us. Yet even the Big Bang, magnificent as it is, doesn't fully answer the ultimate question. What was there before? Or, more profoundly, was there a before in the way we usually think of it? This is where some of the most profound and poetic ideas in cosmology begin to whisper their tales, the Cyclic Universe Hypotheses. These aren't just idle musings. They are serious attempts to extend our understanding of reality beyond the confines of a single, isolated beginning, suggesting instead that our universe might be just one chapter in an endless cosmic story, a breath in an eternal cosmic rhythm. Imagine for a moment the universe not as a one-time event, but as a pendulum, swinging back and forth through eternity. This is the essence of the Big Bounce hypothesis. Our current understanding of the Big Bang, while incredibly successful, points to an initial singularity, a point of infinite density and temperature, where the laws of physics as we know them break down. It's like trying to divide by zero. The math simply doesn't work. The Big Bounce offers a way around this. It suggests that our universe didn't begin from nothing, but rather emerged from the collapse of a previous universe. That prior universe, having expanded to its maximum extent, eventually began to contract under its own gravity, squeezing everything back together until it reached a critical, incredibly dense point, but not a singularity. Instead, at that moment of ultimate compression, it bounced back, initiating the expansion we call our Big Bang. Think of it like a cosmic exhale, followed by an inhale. The universe contracts, reaching a state of maximum density. Then, instead of collapsing into oblivion, it rebounds, like a rubber ball hitting a wall, exploding outward once more into a new cycle of expansion. This idea often finds its theoretical grounding in loop quantum cosmology, LQC, a fascinating attempt to unify general relativity with quantum mechanics. LQC suggests that space-time itself is not continuous, but granular, made of tiny loops. At extremely high densities, these quantum effects become dominant, preventing the formation of a true singularity, and instead forcing a bounce. So, our universe could be the phoenix rising from the ashes of a previous fallen cosmos, carrying forward some of its memories, perhaps even imprints of its structure, into our current era. It paints a picture of eternal renewal, a cosmic heartbeat that never truly stops, just transforms. Then, there's the captivating story of the ekpyrotic and cyclic model, a hypothesis that ventures into even more exotic realms, drawing inspiration from brain cosmology and M-theory. Here, our familiar three-dimensional universe is imagined not as the whole show, but as a brain, a vast, thin membrane, existing within a higher dimensional bulk space, like a sheet of paper floating in a much larger room. In this scenario, our Big Bang wasn't a solitary explosion from a point, but rather the titanic collision of two such cosmic brains. Imagine two colossal shimmering sheets drifting through a hidden dimension, slowly approaching each other. For eons, they might exist in relative peace, until, drawn by some unseen force, they finally meet. The impact, a cataclysmic event of unimaginable energy, would generate the heat and density required to birth a new universe, initiating its expansion. This model offers an elegant alternative to cosmic inflation, which is currently our leading theory for explaining the uniformity and flatness of our universe. Instead of a rapid expansion in the early moments, the ekpyrotic model suggests that these features arise from the slow, gentle approach of the brains over vast stretches of time, smoothing out any irregularities before the collision. The cycle then continues. After the collision and subsequent expansion, the universe would gradually thin out, cool down, and eventually, the forces within the bulk space would begin to draw the brains back together, setting the stage for another collision, another Big Bang, in an unending cosmic dance. It's a story of cosmic tides, where universes ebb and flow, constantly being reborn from the echoes of previous encounters. Perhaps the most mind-bending of these ideas comes from Nobel laureate Roger Penrose with his conformal cyclic cosmology, CCC. This hypothesis takes a truly profound leap, suggesting that the very end of one universe can smoothly transition into the beginning of the next, through a concept called conformal equivalence. Imagine our universe, expanding and expanding, stretching out into an unimaginably vast, cold, and dark future. Stars will burn out, black holes will slowly evaporate away through Hawking radiation, and eventually, all that will be left are photons, particles of light, and perhaps other massless particles, drifting through an empty, featureless void. In such a state, where there is no mass left, Penrose argues that there is no meaningful way to distinguish between different scales of length or time. The concept of bigness or smallness loses its meaning. In this infinitely stretched out, empty, and cold future, Penrose proposes that this state becomes mathematically equivalent or conformally equivalent to the hot, dense, tiny Big Bang of a new universe, a new aeon. It's like taking an infinitely large sheet of paper and through a mathematical transformation that only cares about angles and shapes, not size, making it look exactly like an infinitesimally small point. The end of one eon, stripped of all massive particles, and thus of all intrinsic scales, becomes the Big Bang of the next eon. There's no singularity, no bounce, just a continuous, though conformally distinct, flow. This is a universe that eternally cleanses itself, shedding its mass to be reborn anew, a cosmic phoenix constantly emerging from its own infinitely distant future. Intriguingly, CCC even proposes that there might be faint, observable fingerprints from previous eons left behind in our cosmic microwave background. Tiny temperature anomalies or circular patterns, possibly echoes of evaporating black holes from the universe that came before ours. These are challenging predictions to test, requiring incredibly precise data and careful interpretation. But they offer a tantalizing glimpse into the possibility of empirical evidence for such a profound idea. These cyclic hypotheses, whether they involve bouncing universes, colliding brains, or conformally connected eons, offer us a profound shift in perspective. They challenge the notion of a single, absolute beginning, suggesting instead an eternal dance of creation and recreation, a cosmic story with no true start or end, only continuous cycles of transformation. They remind us that the universe is far more complex and imaginative than we can often conceive, an endless tapestry woven with threads of physics, mathematics, and profound mystery. As we drift deeper into the night, contemplating these grand cosmic cycles, you might wonder, if our universe is just one in an endless chain, how could we ever hope to find traces of those previous existences? What subtle clues might be hidden in the starlight, or etched into the very fabric of space-time that could reveal the secrets of a before we can scarcely imagine? What if our universe is just one among countless others? This question opens doors to profound mysteries that stretch beyond imagination. Our minds, accustomed to linear time, grasp for a before, a quiet prelude to the cosmic crescendo. Yet, the Big Bang wasn't an explosion in space, but rather the astonishing, rapid expansion of space itself, a moment when the entire observable universe was compressed into an unimaginably hot, dense point, smaller than a single atom. It's not like lighting a match in a dark room, it's more like the sudden, graceful unfurling of the room itself from a tightly folded seed. For a long time, this singularity was the edge of our understanding, a cosmic wall that physics equations couldn't quite climb over. What existed prior to this infinitesimally small, infinitely dense point? Did time even have meaning then? It's a question that whispers through the very fabric of our scientific inquiry, much like the gentle rustle of leaves outside your window on a quiet night. But our curious minds, always seeking to peer beyond the veil, have begun to paint possible landscapes for this before. One of the most compelling and widely discussed ideas is linked to a concept called cosmic inflation. Imagine the early universe, just a tiny fraction of a second after the Big Bang, undergoing an unbelievably rapid exponential growth spurt. It's like blowing up a balloon, but instead of taking seconds, it expands to an immense size in less time than it takes for a thought to form. This period of inflation smoothed out the universe, making it look so uniform across vast distances, and flattened its geometry, much like stretching a crumpled piece of paper, until it's smooth and flat. Without inflation, our universe would likely be far more chaotic, lumpy, and perhaps not conducive to the formation of stars and galaxies as we know them. Now, Here's where the idea of the multiverse begins to gently unfurl from the concept of inflation. While our universe underwent a period of inflation that eventually ended, allowing the energy to condense into particles and begin the cosmic journey we observe, what if inflation, in some larger, overarching cosmic canvas, never truly ends everywhere? This is the enchanting theory of eternal inflation. Imagine an infinitely vast, ever-stretching ocean of pure potential, a superinflating space. Within this ocean, pockets of inflation might occasionally slow down or stop, much like bubbles forming and detaching from the surface of a simmering pot. Each of these bubbles, once detached, would then become a self-contained universe, a cosmic infant beginning its own Big Bang. Our universe, with its familiar stars and galaxies, would simply be one such bubble, one unique world amongst an infinite cosmic froth. The before the Big Bang for our universe in this scenario wasn't emptiness, but rather the endless frothing ocean of an eternally inflating megaspace, ceaselessly giving birth to new pocket universes. Each new bubble, each new universe could potentially have its own unique set of physical laws, its own fundamental constants, its own particular blend of ingredients. A cosmic tapestry woven with threads of infinite variety. But eternal inflation isn't the only whisper of a before. Another fascinating proposal comes from loop quantum gravity, a theory attempting to unify general relativity and quantum mechanics. Instead of a singularity, it suggests a big bounce. Imagine our universe, at some point far in the distant past, wasn't born from nothing, but rather emerged from the collapse of a previous universe. This previous universe contracted, shrinking down to an incredibly dense state, not an infinite singularity, but a point of maximum density where quantum effects took over, preventing further collapse. Then, instead of crunching into oblivion, it bounced back out, expanding into the universe we see today. In this beautiful cyclical vision, the before is simply another universe, endlessly repeating the cosmic dance of contraction and expansion, a cosmic breath taken and released over eons. And then there are the even more exotic notions from the string theory and M theory, which often introduce the concept of higher dimensions and brain worlds. Picture our entire universe as just one brain, a vast, multi-dimensional membrane, floating within a larger, higher-dimensional space. The Big Bang, in some of these scenarios, isn't a singular point in time, but perhaps the moment when our brain collided with another brain, or when energy from another dimension leaked into ours. The before then becomes a realm of multidimensional spaces, where universes drift like cosmic ships, occasionally brushing against each other and sparking new beginnings. It's a truly breathtaking vision, like imagining that the surface of your skin is itself a universe, and you are simply one part of a larger, unseen being. These ideas, though still theoretical, paint a picture of a before that is far from empty or silent. Instead, they suggest a vibrant, dynamic cosmic nursery filled with potential and possibility. Whether it's an ocean of eternally inflating space, an echo from a previous cosmic breath, or the gentle touch of another dimensional realm, The space before our Big Bang hums with profound implications for what lies beyond our cosmic horizon. We've begun to explore the potential for these other universes, these other realities, to exist just beyond the reach of our telescopes, perhaps even influencing the very fabric of our own reality. As we drift further into the night, let's next consider what these other universes might actually be like, if they exist, and how they could differ from our own familiar cosmic home. What was there at the very beginning? This ancient question has whispered through the ages long before science offered its own profound imaginings. The Big Bang, as we understand it, describes the universe's astonishing expansion and evolution from an incredibly hot, dense state. But it doesn't tell us what sparked that initial moment, what preceded the cosmic dawn. It's like finding a book open to a thrilling chapter, full of vibrant life and epic events. But the earlier pages are missing, torn away by the sheer intensity of the beginning. Here, our scientific dreams take a truly imaginative turn, leading us into the realm of brain cosmology. Picture, if you will, not a universe born from an empty void, but one that exists within a much grander, more expansive reality. Imagine, instead of our familiar 3 dimensions of space, length, width, and height, there are hidden, curled-up dimensions, unseen and unfelt by us, yet incredibly real. These are not merely abstract mathematical concepts. They are the stage upon which a cosmic ballet of profound elegance might be unfolding. In brain cosmology, our entire universe, with its countless galaxies, its vast cosmic webs, its stardust and all its vibrant life, isn't the whole story. Instead, our universe is like a single, vast, shimmering membrane, a brain floating in a higher dimensional space. Think of it like a delicate sheet of paper or a single film in a colossal stack of films drifting through an immense, unseen ocean. This higher dimensional space is often called the bulk. It's a dimension beyond our current perception, a cosmic ocean where other such brains might also exist, each potentially holding its own universe. These extra dimensions are not something we can simply walk into or point to. They are thought to be incredibly tiny, curled up so tightly that they are invisible to our senses, like a garden hose that looks like a one-dimensional line from far away, but up close reveals its 2-dimensional surface wrapping around itself. Yet, within this hidden complexity, these dimensions provide the stage for brains to exist and move. So, if our universe is just one brain, what about the Big Bang? Here's where the story becomes truly captivating. Instead of a singular, inexplicable burst from nothingness, brain cosmology offers a different kind of origin, a collision. Imagine 2 of these vast cosmic brains drifting through the tranquil darkness of the bulk. Slowly, inexorably, they are drawn towards each other, like 2 colossal, ghostly ships moving across an infinite sea. When these 2 brains finally meet, they don't simply pass through each other. Their immense energies collide, clap together in a spectacular, universe-shattering event. This monumental impact, this grand cosmic embrace, is our Big Bang. This is the core idea behind the ekpyrotic model, a leading proposal within brain cosmology. Ekpyrotic comes from the Greek word for conflagration, or conversion into fire, perfectly capturing the fiery birth of a universe from such a cosmic collision. When these two brains smack into each other, the immense energy released manifests as the matter, energy, and space-time that we observe today. It sets off the expansion, the cooling, and the formation of everything we know. It's not an explosion from a single point, but a cataclysmic interaction between two vast, pre-existing structures. What's particularly elegant about this model is that it offers a way to avoid the troublesome initial singularity of the standard Big Bang. That singularity, a point of infinite density and temperature, is difficult for our physics to describe. In the ekpyrotic model, the Big Bang isn't a point of infinite everything, but rather a moment of immense finite energy density, a bounce between two colliding brains. It's a smoother, more gentle beginning in a conceptual sense, even though the energy involved would be incomprehensible. And the story doesn't necessarily end there. This idea can be extended into the cyclic model, a fascinating evolution of the ekpyrotic vision. What if this collision wasn't a one-time event? Imagine the two brains, having collided and expanded to form our universe, slowly drift apart again. As our universe expands and cools, it reaches a point of maximum expansion, and then, perhaps pulled by some unseen force in the bulk, it begins to contract. This contraction isn't a collapse into nothingness, but rather a slow, stately movement back towards the other brain. They meet again, perhaps trillions of years from now, and collide once more, triggering a new Big Bang, a new cycle of creation and expansion. This means our universe might not have had a true beginning, nor will it have a true end. Instead, it's an eternal dance, a cosmic heartbeat of creation, expansion, and recreation. Our Big Bang was simply the latest bounce in an infinite series of such events, a grand rhythmic unfolding of existence across an unimaginable span of time. The universe breathes in and out, constantly renewing itself through these vast brain collisions. This framework also offers intriguing insights into the fundamental forces. Gravity, for instance, might be unique among the forces. While electromagnetism and the strong and weak nuclear forces are stuck to our brain, like patterns drawn onto our sheet of paper, gravity might be different. Scientists hypothesize that gravitons, the theoretical particles that mediate gravity, could be open strings in string theory, allowing them to leak off our brain and travel freely into the bulk. This could explain why gravity seems so much weaker than the other forces. Some of its power is constantly seeping away into those hidden extra dimensions, interacting with other brains we can't perceive. So, before the Big Bang, there might have been a serene vast bulk, a cosmic ocean of extra dimensions, with ghostly brains drifting silently through it. Our universe, a living, breathing entity, may be just one beat in an eternal cosmic drum, reverberating from the impact of unimaginable collisions. It's a universe that whispers of greater depths, of hidden realms, and of a cosmic story far grander and more intricate than we can yet fully grasp. And as we consider these profound possibilities, Let's next turn our thoughts to another remarkable concept that emerges from these hidden dimensions. The idea that perhaps, just perhaps, our universe isn't alone, but part of a much larger collection of worlds existing side by side in this cosmic bulk. Our cosmic story seems to hit a wall at its very beginning. Traditional cosmology, built upon the elegant framework of Einstein's general relativity, describes an expanding universe that, if we trace it backward in time, shrinks and becomes incredibly dense. This journey back leads us to a point of infinite density and temperature, a singularity. It's a moment where all the known laws of physics break down, a cosmic blank page where our understanding falters. Imagine it like trying to read the very first word of a grand ancient book, only to find that the page itself has vanished, leaving an unanswerable void. But what if this isn't the end of the story? What if that blank page isn't truly empty, but merely obscured by the limitations of our classical understanding? This is where the whispers of loop quantum gravity, or LQG, begin to offer a different tale, a gentler narrative that paints a picture of what might have existed not just at the Big Bang, but truly before it. At the heart of loop quantum gravity is a revolutionary idea. Space itself is not the smooth, continuous stage we often perceive. Instead, it's granulated, much like a finely woven tapestry. If you look closely enough at a piece of cloth, you see individual threads. LQG suggests that space, and by extension space-time, is composed of tiny, discrete units, like individual pixels of reality, or quantum stitches in a cosmic fabric. These are not objects in space, but rather the very stuff of space itself. Picture a delicate, shimmering network of interwoven loops, far smaller than even the tiniest atom. These loops are the fundamental excitations of the gravitational field, forming what scientists call spin networks, or spin foams when time is included. They represent the irreducible quanta of space, the smallest possible units of area and volume that can exist. This minimum size is incredibly tiny, on the order of the Planck length, a scale so minuscule it dwarfs any comparison we can conjure in our everyday lives, billions of times smaller than a proton. Now, let's bring this quantum fabric back to our cosmic origin story. If space cannot be infinitely divided, if there's a smallest possible pixel, then it logically follows that the universe can never shrink to an infinitely dense point. The Big Bang singularity, that moment of infinite curvature and density, becomes an impossibility within the framework of loop quantum gravity. Instead of collapsing into nothingness, the universe, as it contracts backward in time, reaches a point of maximum, but finite, density. It's an extreme crunch, a moment where the very fabric of space-time is stretched to its absolute limit, yet it never tears or breaks down into infinity. Imagine a balloon being squeezed tighter and tighter. Classically, it would pop into an infinitely small point. But with LQG, it's as if the balloon is made of a quantum mesh that, once it reaches a certain compression, simply cannot shrink further. It hits a boundary, not of nothingness, but of pure, quantized space. This crucial insight leads us to one of LQG's most profound and captivating predictions: the Big Bounce. Instead of a singular beginning from an infinite point, Loop quantum gravity suggests that our universe didn't begin at the Big Bang, but rather rebounded from a previous phase of contraction. Picture a colossal cosmic breath. Our current universe is in its expansive exhale. But before this, there was an inhale, a universe that contracted down to that incredibly dense yet finite Planck crunch, and then, with an elegant cosmic sigh, bounced back out into the expansion we observe today. It's like a grand, eternal trampoline where the universe doesn't crash but springs back, full of new energy and momentum. So, what does this tell us about the universe? Before our Big Bang, it suggests the existence of a parent or ancestral universe that was collapsing. Was it similar to ours? Did it have stars, galaxies, perhaps even life? Loop quantum gravity implies a deep symmetry. The laws of physics that govern our expanding universe would have also governed that contracting one. Time would have flowed continuously through the bounce, much like a river passing over a waterfall. The current doesn't stop, it simply changes its environment. This means that the information, the fundamental properties of the universe, are not lost at the bounce. It's not a reset button, but a smooth, albeit dramatic, transition. This pre-Big Bang universe would have had a very specific geometry, much like a mirror image of our own in its contracting phase. The Big Bounce elegantly resolves the problem of the initial singularity, replacing an unanswerable question mark with a dynamic, cyclical, or at least continuous, cosmic process. It offers a more complete and arguably more comforting narrative of our universe's history, suggesting that the cosmos didn't spring from an inexplicable void, but rather transitioned from a previous state, preserving its essence through the bounce. It extends our cosmic story backward, not into an abyss, but into another chapter, an echo of what came before. As we drift deeper into the mysteries of the cosmos, the idea of a big bounce offers a beautiful continuity, a grand historical novel with countless chapters rather than a sudden, unwritten beginning. Perhaps this gentle cosmic rebound holds secrets not just of our past, but also hints at the very fabric of existence itself, guiding us to wonder about the fundamental nature of time and the universe's grand cycles, a thought we can carry with us as we quietly ponder the next piece of our cosmic puzzle. Cosmic inflation precursors. Imagine, if you will, a universe so incredibly young, so unspeakably tiny, that it defies our everyday understanding. It's a universe that exists even before the dramatic, fiery explosion we often picture when we think of the Big Bang. This isn't just a moment of quiet anticipation. It's a realm of profound questions, a cosmic mystery that physicists grappled with for decades. To truly understand the prelude to cosmic inflation, we must first look at the cosmic puzzles it was designed to solve. Picture our vast, beautiful universe today. It's a tapestry woven with galaxies and stars, stretching across billions of light years. When we gaze at the faint glow of the cosmic microwave background radiation, the oldest light we can detect, we see a universe that is remarkably uniform. It's like looking at a perfectly blended smoothie or a vast, calm ocean where the temperature of the water is almost exactly the same, no matter where you dip your hand. This incredible uniformity, this smooth cosmic blend, presented a deep riddle, what scientists call the horizon problem. Imagine 2 points in the very early universe, vast distances apart, so far that light, the fastest messenger in the cosmos, simply wouldn't have had enough time to travel between them. If they couldn't exchange information, couldn't talk to each other, how could they have ended up with almost precisely the same temperature, the same properties? It's like two isolated islands in the middle of a vast ocean, completely cut off from one another, yet somehow experiencing identical weather patterns day after day, year after year, without any prior communication. How could they know to synchronize? The standard Big Bang model on its own struggled to explain this uncanny cosmic agreement. Then there was another curious observation, the flatness problem. Our universe, as best as we can measure, appears to be incredibly flat. Not flat like a pancake, but flat in its geometry. Think of it like this. If you could draw a giant triangle in space, the sum of its angles would add up to exactly 180 degrees. If the universe were positively curved, like the surface of a giant sphere, the sum would be more than 180. If it were negatively curved, like a saddle, it would be less. Our universe, however, seems to be poised right on the knife edge of flatness, a state that requires an exquisite fine-tuning of its initial energy density. It's like balancing a perfectly sharpened pencil on its tip for billions of years without it ever toppling over. For the universe to be this flat today, it must have been unimaginably close to perfectly flat in its earliest moments, a precision that seemed almost miraculous, requiring a deviation of no more than 1 part in 10 to the power of 60. What cosmic mechanism could possibly account for such breathtaking exactness? And finally, the monopole problem. Theoretical physics, specifically grand unified. Theories that seek to combine the fundamental forces of nature predicted that in the incredibly hot, dense crucible of the very early universe, exotic, super-heavy particles called magnetic monopoles should have been created. These would be like individual north or south poles of a magnet, existing on their own rather than always coming in pairs. But despite extensive searches, we haven't found a single one. It's as if a cosmic recipe called for a crucial ingredient to be formed. But when we look in the pot, that ingredient is nowhere to be found. Where did all the monopoles go? Why were they conspicuously absent from our cosmic inventory? These three profound questions whispered through the halls of scientific inquiry, urging physicists to look beyond the immediate Big Bang scenario. There had to be something more, something even earlier, that laid the groundwork for the universe we see today. And this, my dear listener, brings us to the very concept of cosmic inflation precursors, the conditions, the seeds, the initial state that set the stage for inflation itself. Imagine the universe not as an empty void waiting to be filled, but as a restless, seething cauldron of potential. At these unimaginably early times, even before a tiny fraction of a second had elapsed since the universe's absolute beginning, the fabric of space and time was not a calm, still canvas. Instead, it was a frothing, bubbling quantum foam, a realm where particles and antiparticles flickered into existence and vanished again in an instant, a dance of pure energy that underlies everything. This is the quantum vacuum, a concept far richer and more dynamic than any empty space we can comprehend. It's a place teeming with virtual activity, a shimmering, restless sea of possibility. Within this primordial quantum foam, theorists propose the existence of a special kind of field permeating all of space. This is the inflating field, Think of it not as a solid object, but as an invisible, omnipresent energy field, much like the electromagnetic field that carries light waves, or the Higgs field that gives particles mass. In its earliest precursor state, the inflaton field was perched high on an energy landscape like a tiny ball balanced precariously at the very top of a gentle, sloping hill. It hadn't started its descent yet. It was holding an immense amount of potential energy. This high-energy state of the inflaton field is the true precursor. It's the moment before the rapid expansion began in earnest. The crucial scientific fact here is that when a field like the inflaton field is in such a state, holding vast potential energy and distributed uniformly through space, it behaves in an extraordinary way. It generates negative pressure. We usually think of pressure as something that pushes things together, like air inside a balloon. But negative pressure, in the context of general relativity, acts like an anti-gravity. Instead of pulling, it pushes outwards, causing space itself to stretch and expand, not just pushing matter within space, but stretching the very fabric of existence. So picture this precursor state, a universe infinitely smaller than an atom, filled uniformly with this high-energy inflaton field, generating immense negative pressure. It's like a tightly coiled spring, packed with latent energy, waiting for the gentlest nudge to unleash its power. This uniform field, with its inherent negative pressure, was the cosmic fuse, the trigger waiting to be ignited. It was the answer to the horizon problem, because everything started from an incredibly tiny, connected region, then inflated to vastness. It was the solution to the flatness problem, because the extreme stretching of space would smooth out any initial curvature, making the universe appear perfectly flat. Just as blowing up a small, wrinkled balloon to an enormous size makes its surface appear smooth and flat. And it offered a solution to the monopole problem, either by preventing the universe from reaching the necessary temperatures to form them, or by diluting them so effectively across a vast expanse of new space that they became exceedingly rare. In this state, the universe wasn't yet expanding with the dizzying speed of inflation, but all the conditions were perfectly aligned. The stage was set, the cosmic engine was primed, and the whisper of an extraordinary event was about to ripple through the nascent cosmos. It was a moment of profound cosmic elegance, where the problems of the universe found their eloquent solution in the properties of a hypothetical energetic field. And so, in this most primordial of cosmic nurseries, the stage was set for the spectacular act of cosmic inflation itself. Next, we'll explore what happened when that inflaton field began its gentle yet incredibly powerful descent, unleashing a burst of expansion that reshaped reality itself. The nature of primordial space-time before the Big Bang. This is where our journey into the universe's quietest beginnings truly deepens into mystery, into a realm not just distant in time, but utterly alien to our everyday experience. Imagine trying to describe the stillness of the ocean floor, not with water, but with the very fabric of existence itself. Before the Big Bang, before even the spark of creation, the concept of space-time as we know it, that smooth, vast, flexible canvas upon which galaxies paint their dazzling spirals, likely didn't exist in the same way. Our most powerful theories like general relativity, which elegantly describes gravity and the large-scale structure of the cosmos, begin to falter and break down when we rewind the cosmic clock to that infinitesimally small, incredibly dense moment. They point to a singularity, a point of infinite density and temperature, where the laws of physics, as we understand them, simply cease to apply. It's like trying to divide by zero in mathematics. The answer becomes undefined, and our familiar equations lose their meaning. This singularity isn't a physical place in space, but rather a boundary in time, a theoretical wall beyond which our current understanding cannot see. It signals not a dead end, but an urgent whisper that a deeper, more fundamental theory is needed. To glimpse what might have lain beyond that wall, we must descend into the realm where gravity and quantum mechanics, the two pillars of modern physics, finally meet. This is the realm of quantum gravity, where the smooth, continuous fabric of space-time gives way to something far more fundamental, perhaps granular or probabilistic. Think of it like zooming in on a photograph. From a distance, the image is smooth, but up close, you see the individual pixels. At the most extreme scales, incredibly tiny, much smaller than an atom, smaller than a nucleus, even smaller than a quark, lies the Planck scale. This is the theoretical limit where space-time itself is thought to reveal its quantum nature. While nat, the Planck length, an unimaginably small distance of about 10^35 meters, and the Planck time, 10^43 seconds, our familiar notions of space and time as continuous entities might dissolve. Instead, space-time might be woven from discrete, indivisible quanta, tiny, fundamental units, much like the pixels of our cosmic photograph. Imagine the universe not as a boundless, smooth ocean, but as a vast, intricate tapestry woven from countless individual threads. These threads, these tiny units of quantum space-time, would be fluctuating wildly, popping in and out of existence in a chaotic dance known as quantum foam. This foam isn't emptiness. It's a seething cauldron of potential, where the very geometry of existence is turbulent and uncertain. Several profound theories attempt to paint a picture of this primordial state. One such theory is loop quantum gravity, LQG. In LQG, the fabric of space-time isn't continuous, but rather a network of interwoven, discrete loops or spin networks. These loops represent the fundamental building blocks of space, much like atoms are the building blocks of matter. Time, too, emerges from the relationships between these loops. This view suggests that space isn't just empty nothingness, but rather a dynamic quantum structure, and that the Big Bang singularity is resolved not by an infinite density, but by a quantum bounce, a moment where the universe reached a minimum size before expanding, implying a previous universe that contracted into this state. Then there is man's string theory, and its more expansive cousin, M theory. These theories propose that the most fundamental constituents of reality aren't point-like particles, but tiny, vibrating, one-dimensional strings, or even higher-dimensional membranes, brains, existing in a universe with more than the 4 dimensions, 3 spatial, 1 temporal, we perceive. In this view, space-time itself, along with all the particles and forces, arises from the vibrations and interactions of these strings and brains. Our familiar 4 dimensions might be just a slice or a bubble within a larger, higher dimensional bulk. The primordial spacetime in this context could be a realm where these extra dimensions were curled up extremely tightly, or where brains collided to ignite a Big Bang event. These models challenge our very intuition about before. If time itself is an emergent property, a kind of clock that started ticking with the Big Bang, then asking, what happened before, might be like asking, what is north of the North Pole? The question itself might be ill-posed within our current framework. Instead, we might be looking at a different kind of existence, a timeless quantum state, a foundational pattern from which time and space as we know them unfurled. In this primordial state, the fundamental forces we experience today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, would likely not have been distinct. They would have been unified into a single superforce, a cosmic symphony playing a single pure note. As the universe expanded and cooled, this superforce would have progressively broken into the separate forces we observe today, much like a prism separates white light into a rainbow of colors. So before the Big Bang, we don't necessarily picture an empty void, but rather a dense, energetic, quantum fluctuating state. It's the ultimate cosmic egg, not empty, but filled with the potential for everything. It's the unwritten book, where all the stories of stars, planets, and life were implicitly contained. The Big Bang wasn't an explosion into something, but rather an expansion of space-time itself, an unfolding of this primordial quantum realm into the vast, intricate universe we inhabit. Understanding the nature of this primordial space-time is the grand quest of quantum cosmology. It's about finding the initial conditions, the precise settings of this cosmic loom that allowed for the emergence of a universe capable of forming galaxies, stars, and ultimately, us. It's a pursuit that merges the deepest physics with the most profound philosophical questions about existence, origin, and the very fabric of reality. And as we consider these profound possibilities, a deeper question emerges. If space-time itself unfolded from this primordial quantum state, what determined the rules by which it would unfold? What gave birth to the fundamental laws that govern our existence? A profound silence reigned before the grand cosmic crescendo we call the Big Bang, a stillness that stretches our imaginations to their very limits. What whispers were carried on the pre-cosmic winds? What ancient scrolls, if any, held the blueprints for gravity's embrace, for light's unwavering speed, for the delicate dance of subatomic particles? This epic, shrouded in mystery deeper than any starless night, is where we seek the very genesis of the fundamental physical laws that govern our universe. Did they simply exist, timeless and immutable, like a forgotten melody waiting to be sung? Or were they too born from an even more primordial fabric, emerging like the first dewdrop on a cosmic leaf? Imagine the Big Bang, not as a sudden explosion into an existing space, but rather as the very unfurling of space and time themselves. It's like the moment a weaver begins to lay down the first threads of a vast tapestry. Before that moment, our familiar physics, the elegant equations that describe the universe's expansion, the formation of galaxies, and the sparkle of distant nebulae, begin to falter. They whisper of an ultimate boundary, a moment so dense, so incredibly hot, that our current understanding breaks down. This threshold, known as the Planck Epoch, is where the quantum realm, the world of the infinitely small and uncertain, collides head-on with the cosmic realm of gravity, stretching the very fabric of reality to its breaking point. In this extreme environment, the very distinction between energy and matter, space and time, blurs into an almost unimaginable unity. Here, the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were not distinct entities, but perhaps intertwined aspects of a single unifying force, a grand cosmic chord. This is the realm where theories of quantum gravity bravely venture, attempting to weave together the gentle curvature of Einstein's general relativity, which describes the large-scale universe, with the erratic probabilistic dance of quantum mechanics, which governs the subatomic world. It's like trying to find the single, original stream from which all rivers flow, a stream that holds the potential for every waterfall, every winding bend, every ocean. One such ambitious journey into this pre-Big Bang realm is offered by string theory and its more encompassing relative, M-theory. Picture, if you will, not tiny, point-like particles as the universe's fundamental building blocks, but rather infinitesimally small, vibrating strings. Each unique vibration of these tiny cosmic strands gives rise to a different particle: an electron, a quark, a photon. Much like different notes plucked on a violin string produce different sounds. But the profound beauty, and indeed the challenge, of string theory lies in its requirement for extra spatial dimensions beyond the three we comfortably inhabit and the one of time. These extra dimensions, perhaps curled up so tightly they are invisible to us, like microscopic scrolls, could hold the key to how our fundamental laws were established. In this framework, the specific way these extra dimensions are shaped, their geometry, their twists and turns, might determine the precise values of our physical constants and the nature of our fundamental forces. It's as if the universe chose a particular configuration from an almost infinite landscape of possibilities, a cosmic dial set to specific numbers. Imagine an immense library stretching beyond comprehension, filled with books. Each book represents a different universe, with its own unique set of physical laws, its own version of gravity, its own speed of light. Our universe, with its familiar laws, is just one particular volume on a shelf, chosen, perhaps, by a roll of cosmic dice, or by some deeper, yet undiscovered principle. Another captivating narrative emerges from loop quantum gravity, which offers a different vision of the pre-Big Bang era. Instead of continuous, smooth space-time, this theory suggests that space and time themselves are quantized, broken down into tiny, indivisible loops, like the pixels on a cosmic screen. In this view, the Big Bang singularity, the infinitely dense point where our equations break down, is not a true beginning, but rather a big bounce. Imagine a cosmic breath, a gentle inhale and exhale spanning eons. Our universe, according to this theory, might be the result of a previous universe contracting under its own gravity, not to an infinitely small point, but to a minimum quantum volume, before bouncing back and expanding into the universe we know today. In this cyclic model, the fundamental laws could be carried forward from one cosmic cycle to the next, perhaps subtly evolving with each bounce, or perhaps retaining a foundational core. It's a continuous cosmic symphony, with movements of expansion and contraction, each one echoing the last, yet potentially adding new harmonies. Then, there's the intriguing no-boundary proposal by Stephen Hawking and James Hartle, which suggests an even more profound conceptual shift. It proposes that the universe didn't begin with a distinct starting point in time at all. Instead, it emerged from a state where space and time were intertwined in a way that defied our conventional understanding of a beginning. Imagine walking towards the North Pole. As you get closer, the concept of north starts to lose its usual meaning. There isn't a point before the North Pole where north points in a different direction. It's simply the apex. Similarly, the no-boundary proposal suggests that the universe's initial state was like the North Pole of space-time, a smooth, finite realm without sharp edges or a definite beginning in time. In this gentle emergence, the fundamental laws would not have been suddenly switched on, but would have smoothly coalesced as space-time itself, unfurled, like a flower slowly opening its petals to the sun, revealing its inherent structure and rules as it blossoms. These theoretical endeavors, while vastly different in their approaches, all share a common thread. They aim to understand if our fundamental laws are an inevitable consequence of deeper principles, or if they are but one manifestation among countless others. The fine-tuning problem gently nudges us in this direction. The observation that many physical constants seem exquisitely set for the emergence of life. If, for instance, the strong nuclear force were just a tiny bit weaker, atomic nuclei wouldn't hold together. If gravity were slightly stronger, stars would burn out too quickly. Is this a coincidence, a grand stroke of luck, or a hint at a deeper structure in the pre-Big Bang realm? Perhaps in the infinite library of the multiverse, where an endless array of universes bloom, each with its own unique set of laws. Ours is simply the one where life, and therefore consciousness, could naturally arise to ponder its own existence. As we drift through these profound cosmic possibilities, we find ourselves at the very edge of human knowledge, gazing into the profound depths of creation. The origin of the fundamental physical laws, whether they are eternal principles or emergent properties of a primordial epoch, remains one of the most tantalizing mysteries. But it is in this very mystery, this gentle uncertainty, that the true wonder of cosmic exploration lies. These scientific explorations of how physical laws emerged lead us to even deeper questions that transcend science itself. Beyond the mathematics and theories lies a profound mystery that touches the very essence of existence. What existed before the universe as we know it began its grand, accelerating dance? This is perhaps the most profound question that has ever whispered through the chambers of human thought. A question that stretches the very fabric of our imagination and brushes against the limits of our understanding. Imagine, if you will, standing at the edge of a vast, silent ocean, shrouded in a mist so thick you cannot see the horizon. This mist is the boundary of our current scientific knowledge, and beyond it lies the mystery of absolute origins. The Big Bang, as our prevailing cosmological model describes, wasn't an explosion in space, but rather an expansion of space itself, bringing with it time, matter, and energy. It's like the opening pages of a cosmic storybook, where the first words are written and the narrative begins to unfold. But what about the blank pages before that? What about the author, or the ink, or the very concept of a story. Now our most sophisticated telescopes peer billions of years into the past, capturing the faint, ancient light of the cosmic microwave background radiation, the afterglow of the universe's infancy. This is the earliest moment we can truly see and study, a snapshot from just 380,000 years after the Big Bang. But before even that, before atoms could form, before light could travel freely, lies an era known as the Planck Epoch. This was an unbelievably fleeting moment, lasting only 10 to the power of minus 43 seconds. 0, 0, 1 seconds after the Big Bang. It's a duration so infinitesimally small, it's almost beyond comprehension, like trying to measure a thought. In this epoch, the universe was incredibly hot and dense, a cauldron of unimaginable energy. And it's here, at this very threshold, that our most trusted theories, general relativity, which describes gravity on cosmic scales, and quantum mechanics, which governs the subatomic world, simply break down. They become incompatible, like two different languages trying to describe the same profound secret. It's as if the very rules of the game we understand no longer apply, leaving us with a beautiful, awe-inspiring silence. So, what does it mean to talk about before the Big Bang? Did time even exist? If time began with the Big Bang, then the word before loses its conventional meaning. It's not a previous moment in a timeline, but rather a conceptual frontier. This idea is profoundly unsettling, for it challenges our most fundamental intuition about cause and effect. If there was no time, how could there be a cause for the universe's beginning? It suggests a causal origin, an event that simply was, without a preceding temporal step. This leads us to the most perplexing question of all. Why is there something rather than nothing? What is nothing? Is it truly an absolute void, an absence of space, time, matter, energy, and even the laws of physics themselves? Or is nothing a more nuanced concept? Quantum mechanics, with its strange and wonderful rules, offers a tantalizing hint. Even in what we perceive as empty space, quantum fields are constantly fluctuating. Particles momentarily pop into existence and then vanish, borrowing energy from the vacuum in accordance with Heisenberg's uncertainty principle. This phenomenon, known as quantum fluctuations, suggests that even true nothingness might be a vibrant, effervescent ocean of potential, teeming with virtual particles and transient energies. Could the universe, in some profound sense, have emerged from such a quantum foam, a cosmic seed spontaneously manifesting from the ultimate nothing? Twice. Some cosmological models venture beyond the Big Bang, proposing scenarios that attempt to answer the before. One such idea is the Cyclic Universe, or Big Bounce model. Here, our universe isn't a singular event, but one in an infinite series of expansions and contractions. Imagine the universe as a cosmic accordion, expanding to a maximum size before gravity eventually pulls it back together, compressing it into an incredibly hot, dense state, perhaps even smaller than the Planck Epoch. and then bouncing back into another expansion. This model offers an eternal universe, avoiding an absolute beginning. But it still leaves us wondering about the first bounce, if such a concept even applies in an infinite cycle. It's a grand repeating symphony, without a clear start or end, each note a universe unfolding. Another fascinating concept is the multiverse. This theory suggests that our universe is just one of countless bubble universes floating within a much larger, eternally inflating space-time, often called the bulk or the multiverse fabric. Imagine an endless ocean where countless bubbles are constantly forming and drifting apart. Each bubble is a universe, potentially with its own unique laws of physics and fundamental constants. In this scenario, the question of origin shifts. It's not our universe that had an absolute beginning, but perhaps the multiverse itself. Or perhaps the multiverse is truly eternal, an endlessly fertile cosmic generator. This idea provides a captivating answer to the fine-tuning problem. The observation that our universe's physical constants seem perfectly calibrated for the emergence of life. If there are countless universes, then it's not surprising that at least one of them, like ours, would possess the right conditions. These are not just scientific hypotheses, they are deeply philosophical inquiries. They force us to confront the very nature of existence. If the universe emerged from quantum fluctuations, does that imply a fundamental randomness at the heart of reality? If there are infinite universes, does our own lose its unique significance, or does it become even more precious? Does the concept of a creator remain relevant if the universe is part of an eternal cycle or a vast multiverse, or if it emerged spontaneously from a quantum vacuum? Understanding absolute origins requires us to stretch beyond the comfort of our current physical laws into realms where quantum gravity might offer a unified description of reality. Theories like loop quantum gravity and string theory are ambitious attempts to reconcile general relativity and quantum mechanics. While incredibly complex, they hint at a universe where space and time might not be continuous but granular, like tiny pixels at the most fundamental level. Perhaps before the Big Bang, space-time itself existed in a different, more fundamental state, a state we are only just beginning to conceptualize. The profound implications of absolute origins touch upon our very identity as conscious beings. To seek the beginning is to seek our own beginning, to understand the fundamental ground of our being. It is to acknowledge the vastness of the unknown and to embrace the humbling realization that the universe holds secrets far grander and more intricate than we can currently grasp. This eternal quest for understanding, this gentle probing into the cosmic abyss, is a testament to the insatiable curiosity that defines us. These philosophical questions, profound as they are, find their answers not in pure thought alone, but in observation. The universe, in its quiet wisdom, may have left us clues, faint whispers from that primordial moment that we are only now learning to hear. Future observational signatures are not about directly peering into the time before the Big Bang, for that elusive moment is forever shrouded from our direct gaze by the very fabric of our universe's beginning. Instead, it's about becoming cosmic detectives, patiently sifting through the most ancient evidence left behind, searching for faint whispers, ghostly imprints, or subtle echoes from a realm beyond our own cosmic dawn. Think of it like trying to discern what happened in a room before the dust settled after a grand explosion, by carefully examining the patterns in the scattered debris, the vibrations in the air, and the faint scorch marks on the walls. Our greatest witness to the early universe, and therefore our best hope for finding these pre-Big Bang clues, is the cosmic microwave background, or CMB. Imagine the CMB as the universe's oldest baby picture, taken when it was just a mere 380,000 years old, a tiny fraction of its current age. This ancient light, a pervasive glow that fills the cosmos, tells us a story of a universe that was incredibly hot, dense, and remarkably uniform. Yet, within this nearly perfect uniformity, there are tiny, almost imperceptible temperature variations, like the minuscule ripples on a perfectly calm pond. These ripples are incredibly important, for they are the seeds from which all the galaxies, stars, and eventually us would grow. Now, for the cosmic detective, these ripples are not just random noise. They might hold secrets, not just about the moment of the Big Bang itself or the period of rapid expansion called inflation that followed, but perhaps before it. Scientists pore over the CMB data, looking for anything that deviates from what standard cosmological models predict. These deviations are called anomalies, and they are like intriguing smudges or unexpected patterns on our ancient cosmic photograph. One such anomaly is the famous cold spot, a vast, surprisingly cold region in the CMB that seems just a little too large and a little too cold to be easily explained by random quantum fluctuations in the early universe. Could such an anomaly be a scar, a subtle imprint left by a collision with another universe, or a remnant from a previous cosmic cycle that somehow crossed into our own? It's like finding a strange, unexplainable mark on a freshly painted wall. It might just be a random splash, or it might be a clue about what happened before the paint was applied. Another fascinating idea, proposed by the brilliant physicist Roger Penrose, comes from his theory of conformal cyclic cosmology, or CCC. This theory suggests that our universe isn't a one-off event, but rather one in an infinite series of eons, each beginning with a Big Bang and ending with an infinitely expanding empty universe. In this model, the infinitely distant future of one eon becomes the Big Bang of the next, like a cosmic baton pass. Penrose and his collaborators predict that if this is true, the gravitational waves emitted by supermassive black holes evaporating in the previous aeon would leave a very specific signature on our CMB. These would appear as faint, concentric circular patterns of slightly elevated temperature variations, much like the ripples spreading outwards when a pebble is dropped into a pond, but on a cosmic canvas. Finding such a pattern would be like finding the perfect subtle watermark on an ancient scroll, proving its true origin from a distant time. Beyond the subtle variations in temperature, we also look for other characteristics of the CMB, such as its non-Gaussianity. If the distribution of these tiny temperature fluctuations isn't perfectly random in a statistical sense, what we call Gaussian, it could indicate that something very exotic happened in the earliest moments, perhaps even before inflation began, or that inflation itself was influenced by pre-existing structures or fields. These non-Gaussianities are like finding that the scattered debris from our explosion analogy isn't spread out randomly, but shows a subtle, underlying pattern, a hint that something more complex was at play. But the CMB isn't our only tool. The universe also speaks to us through gravitational waves, ripples in the very fabric of space-time itself. Imagine space-time as a vast, invisible ocean. Any incredibly violent event, like colliding black holes or the Big Bang itself, sends out waves across this ocean. Unlike light, which gets scattered by the dense, hot plasma of the early universe, gravitational waves travel unimpeded, carrying information from moments far, far earlier than the CMB, potentially all the way back to the Planck Epoch, or even before the Big Bang singularity, if it was actually a bounce, rather than a beginning from nothing. Cosmologists predict that a background of primordial gravitational waves would have been generated during the inflationary epoch following the Big Bang. Detecting these faint echoes, perhaps through incredibly precise measurements of the CMB's polarization, the direction of its light waves, or directly with future space-based observatories like LISA, would be like listening to the universe's most ancient symphony. The specific tune, the spectrum, and the polarization pattern of these primordial gravitational waves could tell us a profound story about the energy scales involved in inflation, and crucially, might even hint at the physics that preceded it. If our universe emerged from a bounce, a contraction followed by an expansion, instead of a singularity, the gravitational wave signature would be distinct, a unique fingerprint left by the cosmic turnaround. This quest for future observational signatures is about more than just satisfying scientific curiosity. It's about pushing the boundaries of our understanding of existence itself. It's an epic journey into the very first moments, a patient, quiet listening for echoes of a time almost beyond comprehension. We are like patient archaeologists, meticulously uncovering fragments of an ancient cosmic tapestry, each signature a precious thread that might one day help us weave together the complete story of our universe's true origins. The signals are incredibly faint, buried under layers of cosmic noise, demanding the most exquisite precision and unwavering patience. And as we continue this patient listening, this cosmic detective work, we are constantly refining our tools, our theories, and our understanding. Each new piece of data, each unexpected anomaly, brings us closer to painting a more complete picture of the universe's earliest moments, and perhaps what came before. In the quiet of the night, as we drift toward slumber, it's comforting to know that our universe, in its own gentle way, might just be trying to tell us its oldest, most profound secret. And so, my dear one, we've journeyed together to the very edge of our understanding, a place not bound by maps or calendars, but by the quiet whispers of thought. We peered into a time, or perhaps a non-time, before the grand unfolding, before the brilliant flash that painted the cosmos with stars and galaxies. It's a concept so vast, so profoundly still, that our minds only gently graze its edges like a fingertip tracing the soft curve of a moonlit cloud. We considered an exquisite nothingness, a perfect silence where space had yet to stretch its boundless limbs, and time had not yet begun its steady, rhythmic march. Imagine that deep cosmic breath held, a moment of infinite potential, pregnant with all that would one day burst forth in a symphony of light and matter. It wasn't desolate emptiness, but a fullness brimming with the promise of existence, a silent prelude to the grandest story ever told. we thought about the strange, beautiful notion of an infinite density, a single boundless point holding all the future universe within its impossible grasp. A place where all the energy, all the particles, all the fundamental forces that would ever dance into being were gathered in one magnificent, compressed secret. It challenges our everyday logic, doesn't it? It invites us to stretch our minds beyond the familiar, to embrace ideas that feel like soft paradoxes, yet hold the deepest truths. And then, perhaps, we allowed ourselves to wonder if there were cycles, grander than anything we can perceive, universes blooming and fading, breathing in and out like an eternal cosmic heart, a vast, gentle rhythm of creation and dissolution, where our own universe is but one exquisite note in an unending melody. The thought is comforting in its vastness, suggesting a continuity, a flow that transcends even the most monumental beginnings. What a beautiful mystery we've explored tonight. It's not about finding definitive answers, but about the profound, comforting act of asking the questions themselves. It's about letting our imaginations unfurl in the quiet darkness, reaching out to touch the fabric of existence or non-existence before it began. This journey, my dear, reminds us of the endless wonder woven into reality. It shows us that even in the absence of form, in the quiet before the word, there is a magnificent, awe-inspiring potential. It's a testament that the universe's story is far richer, more intricate than we could ever grasp with our waking minds. And isn't that a profoundly peaceful thought? To know there is so much more to marvel at, to gently ponder just beyond the veil of our immediate perception. As you drift now, nestled in your soft bed, let these vast, gentle ideas settle like starlight in your mind. The before the Big Bang isn't a place of fear or emptiness. It's a realm of pure, unadulterated possibility. It's the gentle hum of everything waiting to become, a canvas waiting for its first stroke of paint, a song waiting for its first note. There's a deep, soothing calmness in recognizing that even the greatest beginnings arose from a profound stillness. This quiet reflection doesn't dim the wonder of our vibrant universe. Instead, it deepens it. It reminds us that our own existence, our brief, beautiful moment in time and space, is part of an immeasurably grander narrative. We are echoes of that initial potential, fragments of that magnificent, silent secret. And in that connection to something so ancient, so foundational, there is an immense sense of belonging. You are not just here. You are woven into the very fabric of everything that was, is, and will be. Feel the soft darkness around you now, my precious one. It's not an empty darkness, but a gentle, embracing quiet, much like the profound stillness we imagined before the universe took its first breath. Let it cradle you. Let your thoughts, like little stars, gently twinkle and fade, carrying the echoes of our journey to the very edge of time. There's no need to grasp at understanding everything. Not tonight. Just let the feeling of it all wash over you. The quiet wonder, the gentle mystery, the boundless potential that resides in the unknown. It's a comfort, truly, to know that some of the most beautiful truths are found not in definitive answers, but in the profound, open-ended questions themselves. As your eyelids grow heavy and your breath slows to a peaceful rhythm, know that the universe's most wondrous stories continue to unfold, not just out there, but deep within the quiet chambers of your own sleeping mind. The journey of exploration, the gentle dance with big ideas, doesn't truly end when your eyes close. Instead, it transforms. In the realm of dreams, where imagination takes flight without the constraints of logic, you can continue to drift through the potential of the pre-universe, to witness its quiet, expectant hum. You can explore the vast, silent landscapes of possibility, or simply rest in the comforting thought of a universe that once held all its magnificent secrets close. So let your mind wander where it will, carried on the soft currents of sleep. May your dreams be filled with gentle wonders, with quiet starlight, and with the boundless, reassuring peace of all that is and all that was before. Rest now, my dear. Rest deeply and well. The universe, in all its mystery and magnificence, watches over you. Good night, my sweet one. Sleep peacefully.